square estimation. Here you see, on these two tables here, more or less a summary of what we did last week. So that's the starting point, right? So we have a linear regression model, and please recall that this assumption is not as restrictive as it seems, right? So our endogenous variable y is just, we want to express y as a linear combination of some exogenous regressive x. Okay, and u is the residual. Okay? We don't know beta, so that's our task, so to say, to find a good approximation of that process by estimating the betas. Right? Estimating means in that chapter just, we don't care about statistics, we just find the beta that minimize the sum of the squared residuals that are implied if we plug in some certain estimates of betas. Okay, so in matrix notation, this is just x, y is x beta with u, and what we did is we used, we just maximize this here. We take the first order conditions, with the goal function that the sum of squared residuals are minimized, and we saw that, well, this is a well-known formula of the ordinary square estimation, which directly is implied by this first order condition. Yeah? We also noted that equivalent to the first order condition, that we want to minimize the sum of squared residuals, is that moment condition, that we wanted to have that the residuals are orthogonal to all the regressors. Right? That exactly gave the first order condition that we derived from minimizing the square residual. So this is a kind of equivalent, right? And this equivalence of orthogonality of u and x and the least square criterion, this is more or less, now exploited by this geometric interpretation of least square estimation, right? So what you see is that ordinary square estimation implies orthogonal projection of y in, and now it's a new number, we call it delta x, or span of x in the more math term. And this is just the space or the set of all linear combinations of these regressors. You see, that's the starting point. We want to express our endogenous variable as a linear combination of regressors. Okay? And if we plug in some estimates for the betas, what you obtain is a forecast y hat here that is nothing but a linear combination of the x's, right? Our predicted or forecasted value of y hat, is just beta hat plus beta 1 hat plus x1 and so on and so on and so on. So our predicted values are nothing but a linear combination of the regressors, right? This is what is here, right? If you plug in the formula for beta hat, which we derived here just by math, right? We obtain this here, this lengthy matrix. And this lengthy matrix tells you, if you just start with y, your endogenous observation, how to get the predicted value. And we know already the predicted value is a linear combination of the regressors. In other words, it lies in the space of all linear combinations of blah blah blah, this delta of x, or span of x. Okay? So the beauty is now that you see this lengthy matrix here is actually a projection matrix. We call it a projection matrix because it's another word would say it's idempotent. So if you just square p, it doesn't change. Okay? We did that, just multiply it out, and you see all the x cancels out, and you see p squared is nothing but p. And moreover, what's also easily done is, if you multiply p with x here, you see that also cancels out, and it's just px is just x. So what does that mean? So the aim of last week was to clarify that this here is a very, how would you say, a very plausible indication of the idea of projecting the y into that delta x space of all linear combinations of the vector. Because look here. Suppose your observation is already a linear combination of the x. So it is in that space x, right? And now you want to make a prediction for that endogenous observation, which is actually already a linear combination of the x. So what is the optimal prediction? You just take that linear combination, right? Okay, you have some observations and you want to predict, and you want to express these observations just as a linear combination of k endogenous regressors. Okay, if this is by chance perfectly possible because it already is a linear combination of it. Yeah? So just assume that for one endogenous observation, this is just identical with x1, right? Strange example, but well, just assume, right? And that clarifies that, well, if my endogenous variable is already in the subspace, projection on that subspace, of course, just, replicates my observation. Okay? Well, that is the idea of if you have here, if that vector of this endogenous observation here would already lie into that space. Well, if this black arrow here would already be in that light here, then projection would just replicate that, right? This is what this result here tells you. And this is what this figure here should clarify. And the same here is the projection idea. So if I take some variable here, y, and I project it in that plane, so I express y as a linear combination of these two axes. So it's y hat then. And now I say, maybe I can do better. Maybe I can do, maybe now I want to express the y hat again as a linear combination of the axes. So in a way, I run the least square regression twice. Okay? So what happens? Well, nothing. Because if I regress the y hat on the axis, then just exactly the same result will appear. Right? Because y hat is already in that plane. So if I project something which is in the plane, well, nothing happens. Okay? So I guess Lea tried to do this here with a projector, right? So and I also tried to do that last week, right? That if you have a three-dimensional thing and in here is something like, oh, here's the shadow of my hand, well, okay, this here is now really different. This is p times x, and this is here this is y, right? Now I projected in that plane, so this is px. But if I use now a picture of my shadow hand here and project it again, then it would just replicate that, right? It wouldn't change because it's already two-dimensional, right? So this is this idea. But it's not only a projection; it is also, as you can see from the figure, it is an orthogonal projection. And here come that moment conditions from the square estimation, right? Orthogonal means here, mathematically, that these two matrices here, which give me the u hat and the axis, that these are orthogonal on each other. If you multiply that out, it's just 0. Right? It's p times the identity matrix, that's p minus p squared, is p minus p 0. Okay? The proof of this is so trivial, right? But what that means, that this here shows that this vector here, u hat here, is orthogonal to the x. Right? And this is when you remember, geometry from school, right? Of course, the orthogonal distance is the shortest distance between two vectors, right? If I want to go from point A to point B, the shortest distance is just going straight, right? Orthogonal. And this is exactly here. This is the small here. If you have this point and you want, from this point, you want to go to that light plane, the shortest direction, the smallest u, the least squares, is just the orthogonal way. You go just right down. Okay? So this is the equivalence of geometrical projection, so just geometry, and mathematical optimization, which give us this formula in the first place. Okay. Well, you might say, yeah, oh, yeah, more or less interesting stuff, you know, I already know that formula from Econometrics Bachelor, so what does that help me now, that I can reinterpret it as a projection, right? Yeah, well, you know, I think it helps a lot, because here are some results which might not be standard for Bachelor Econometrics, because it's not so easy to see if you just work with equations and first order conditions and things like that. This reads, interpreting OLS as projection reveals results 4. And what we did is, well, what we showed on this slide here, that if we get used to this projection matrix and this idea of projecting, then we get one very nice result, that if we multiply the axis with some non-singular transformation matrix, so some non-singular matrix A, so the inverse exists, therefore it's not singular, right, or regular, invertible, then you can easily show that, well, if you just write down the projection matrix that corresponds to that new set of regressors, x times A, so if you write down what Pxa is, then you see that all these A's cancel just out, right? Just you know, plug it in and you see how they cancel out. So in other words, Px is the same as Pxa. So whether you regress y on x or on these modified set of regressors xa just changes nothing for y hat, and also nothing for u hat. Because u hat and y hat, so my predicted value and the estimated residual of my regression just depend on p. And if p doesn't change, well then y hat and u hat does not change. And this is that result here. Okay. We already talked a little bit about these invariants of transformations right at the beginning, and you might have heard that already in the bachelor thesis, because if you look at that formula here, right, you immediately see, if I would just multiply, for example, the x with some number, yeah, if I just rescale my observations, right, then you see immediately how things cancel out, right? Respectively, they do not exactly cancel out, because look, y hat and u hat are invariant, so it doesn't help you for your forecast or something like that, or for the fit of your model. And when you multiply your axis with some non-singular matrix, but it of course changes the beta hat, right? If you rescale your axis here, look, if you multiply the x with 2, then of course, you know, there's something left. Here you have 2, 4, minus 1, 1 over 4, times 2, 1 over half. So if you multiply x with 2, the beta is half, right? You see that already from that formula here. And this is a generalization of it. You see how the beta changes. If I go from the model y depends on x beta to the model y depends on xa beta, then the beta changes, right? And it's clear how it changes, because you just have to plug it in the formula, right? So this is the least square formula here, but not for x, but for xa. And again, you see if you apply the rules for matrix algebra, these 5 rules we need in this lecture, right? Then you can see that what cancels out in this here, that is exactly what remains. And this is a generalization of what I did here for multiplying x with 2, right? Multiplying x with 2 halves beta, 1 over 2 halves, right? So this is a very generalization. So, you know, while I see immediately when you multiply just the regressor with the number, like 2, yeah, or if you go from euros to dollar or something like that, just rescaling with a number, well, this is easily seen, and it's also easily understood that that shouldn't change anything, right? So, beyond scaling, right? So these non-singular matrix transformations, these are, you know, far more general and not so obvious, right? Here, for example, that was the example here, a very useful thing. You see this matrix here, A, is, now I say obviously, hoping that it's really obvious for you, is the non-singular matrix, right? Because the determinant is non-zero, because the rows are, the columns, rows are obviously linear independent, right? So you could derive the invert matrix of A, right? It's a tedious thing, we don't do it, right? That's good. You know it exists, and therefore this here applies. And what this matrix here does is you multiply it with your, in this example here, to your regressor matrix X. You see what happens is that you just that the first row here is unaffected because it is 1, 1, 1, 0, 0. But the second row is just the X minus the mean of the X. So what that A matrix does is you do the same regression as before, the constant and these two matrices and these two regressors, but you use the demean verb. Right? That's one. Okay, so demeaning in the first step doesn't change your predicted value. Right? So if you have a regression, y on some regressors, make predictions for it, and somebody comes around the corner and say, hey, maybe we could improve our forecasts if we just take the demean values. Then you know already, come on, no, that doesn't help, that doesn't change anything. Right? You would numerically obtain exactly the same results for your y hat. Okay? That's it. Okay, so that was one result. Very useful. The orthogonality projection property here, that is at the very heart of a very important theory related to least square regression, the Frisch-Wall-Glover theory. Very old, very famous, very useful. It showed that it's possible, of course, because of that orthogonality thing, to concentrating out regressors, as we named it. Here, that's the Frisch-Wall-Glover theory. This, as I already told you, right, the proof is rather tedious, but if you look at it, the only thing which is always done, the only argument is always, this is a projection, this goes to 0 because it's an orthogonal projection, it is always the same. Right? So the mathematical complexity is not very deep, but it's a lengthy proof, and this is just boring. Right? This is why I don't do it here. Okay? It's not because it's so super complicated, it's just not worth the time. Okay? But the result, that's important to memorize and to understand what that means, because it tells you, so here is a matrix notation, right? So the m's are here, the m's here, right? And you see that it's useful, to indicate here that this is the M matrix for this first set of regressors x1. So we regress y in the first step on only the variable x1. We take the residuals, and these are the residuals of it. Because the residuals of a least-square regression can be obtained by multiplying your observation y with this M matrix. So if you have something like this means just these are the residuals from the regression of y only on the regressors contained in x1. x2 forgotten for a moment, right? And Frisch-Wall-Glover tells you can concentrate out x1, so you can, in a sense, if you're only interested in beta 2, you don't have, it doesn't matter whether you take this model here, this complicated long model with a lot of regressors, right? Or if you proceed in 2 steps. If you first regress y and x2, you see, only on x1, take the residuals, because these are the m's here, and then regress residuals of these first step regression on each other. If you do this, then numerically you get the same result for beta 2, and also beta 2, by the way. Okay? proof, as I said, just is based on these two things here. So, application of this is, for example, the seasonal dummy thing, right, that you can either adjust if you use linear regressions. You can, it doesn't matter for your results if you put in all the seasonal dummies always in your regressions, or if you seasonally adjust all your observations in the first step and run your regressions with a seasonally adjusted. So it doesn't change anything. Okay, so same for time trend adjustments. And we use this result also for the effect of regressing y on an impulse dummy. And remember, an impulse dummy is a dummy variable that is only one at one time or one observation. Yeah, this is called because it's impulse, because it's only one and then zero always all the time. So you see it comes. So the spirit is from time series analysis, right? When this would be period 1, 2, 3, 4, 5. So we have one impulse in period 3, one shock, and that's it, right? But you can also think of cross-section applications, of course, when this is just persons 3, right? And what this fishwalk level tells you is, and this was this slide here, where we used the equivalence of estimating the regression with such an impulse dummy, ED, that just picks out the D observation, right? And leaving just observation D out. That this is really equivalent. That's the consequence of the fishwalk level theory, and we use this result to talk about influential observations having a high leverage. So remember, here, this is one critique of the least-square regression that is too sensitive to outliers, to observations with a high leverage. So if x here, this x variable here, is a high leverage point because it's very different from the bulk of the observations, right? Here only in one dimension because you have a two-dimensional thing, right? We discussed that in practice when you have more than 2 regressors, when you have 10 or 20 regressors, cross-section analysis, a lot of demographics and so on, then points with high leverage are not so easily spot. Yeah, because you can't look at the 20-dimensional scatter plot and spot, this is an observation with high leverage. Yeah? Sometimes it's more complicated, right? That in many dimensions, an observation looks somehow typical, right? Standard. But the combination of all regressors, then it's atypical, right? So you can be average with respect to all demographics, but the combination of your demographics are unusual. Okay? So, not so easy to spot. This is why these leading one-out regressions are popular if you really care about your robustness of your results, right? What you don't want to have is that all the results depend just on one observation, right? And you see, if you have not so many observations, this is often a critique, right? If you run a regression with 1 million observations, then it's not so plausible that everything depends on one observation, right? But if you have only 100 observations, like here, you're right, then you see that leaving that point out here changes the slope of the regression line significantly. Okay? So this here shows you that it takes 2 things to be an influential observation. First one is that the x's here are somehow unusual, and this is here more or less here given by this expression here by the axis. And the second one is that this point here lies actually far away from your regression line, right? So this point here would not be influential if it would be here, right? What is the line without? With point excluded? With point in, yeah. It would be here, yeah, then it would not be influential. Because, you see that already, yeah, that the regression line would not change a lot if this point would be here. And this second component of influential observation what is the extra impact of these observations on the regression line. So these are two important implications which become, I think, particularly plausible, and understandable if you have understood this projection idea. Okay? So there's a third thing which becomes more clear if you use projections, and this is the projection of fit thing, the goodness of fit thing. Okay, this is something you should know from bachelor geometrics. You all know what an R square is, right? And this is the derivation of the R square, but now coming from this geometric interpretation. Yeah. Again, you see that, we already talked about that. This orthogonal projection, this is a projection that minimizes the distance of y to the S-plane. Right? So this here, if you take just now the sum of the squared residuals here, the estimated residuals, right? We call this the sum of squared residuals, SSR, right? And you see how this length of this vector here, the longer that vector, the larger the residual, right? And this is the length of the vector. This is just geometry, right? Then you see, we're using the Pythagoras, that this is a rectangle here, right? 90 degrees. So the length of the y is the sum of the squared length here of this is the squared length of that plus the squared length of that. This is here the variance decomposition, right? Interpreted geometrically. Okay, we call this the total sum of squares, and this here in the book of Davis and McKinnon is called the explained sum of squares. There are variations in textbooks about that. Okay. So, and you see this can be interpreted as a variance decomposition, therefore, of our endogenous variables, and this is how you do it normally. You say, okay, if I just divide now by y squared, then I define here the R square of the regression as explained sum of squares divided by total sum of squares, right? Or which is just equivalent 1 minus this here. And you see that the explained sum of squares, look, what is that? Here, this is this x beta hat. X beta hat is that one here. It's px. So this is why this here shows up. Right? So this formula, this reinterpretation of the R square shows you two things. Okay, first of all, of course, this is already known, right? The R square, just by how you derive it, right? This must be always between 0 and 1. Okay, always. You have only positive numbers, and this here is, if you look at that here, this here is always a shorter vector than that one. Right? The length of this here is always shorter than that. Trianguli in equation O. Right? Okay, so this explains why it's smaller than 1. Or not larger than 1. Okay? And because this is the explained part here, right? If the explained part is more or less has the same length or variation as the actual endogenous variable, then of course, if this is 1, we have a perfect fit. Okay? This is the maximum value of R squared. The higher R squared, the higher is a fraction of the explained variance by the model. That's a typical exam question in the bachelor. This is the R square of regression. How can you interpret it? Right? And the answer is, well, if it's 70.0, 0.7 or something like that, say an R square of 70% means that 70%, that the model, my regression model, can explain 70% of the variation in the endogenous variable. The variation on the variance or whatever. Okay? If this is 0, yeah, then look at the numbers, then obviously, you know, this is here 0, and all the residuals are identical with the endogenous variable, so you explain nothing about it. Okay? So this is all known, right? This is just factual econometrics, at least the results, right? So, but what you see now is, when you remember what we already showed here for our non-singular transformation and all the things we derived from that idea by interpreting the least square estimation as a projection, what you see is already that the R square is invariant under non-singular linear transformations of X, right? Because this is what we showed here, right? Here we have the length of y hat divided by the length of y. Y hat does not change if we replace the x by x times a, these non-singular transformations. Okay, but if y hat doesn't change, y does also not change because we do a non-singular transformation of x and not of y, then this just remains unchanged. Okay? So this very general result here, that the R squared does not change under non-singular linear transformation of x, right? This is, you know, an immediate consequence of this projection thing here. Okay, I don't know how to prove this. It's not so easy to prove this with the techniques you know from bachelor. Right? And also obvious from that formula here is that if you just change the scale of y, so multiplying equals 2 or something like that, then obviously here if you look at the definition of y hat and here and the definition here of y, if you multiply that with 2, then that would also show up here, and it will just cancel out. So a change of scale, right? If you do a regression on something in dollars, and then you take a constant exchange rate and you reorganize everything now in euro, then the R square will change. Okay? Okay. Please recall, you know, in order to have this variance composition, we need that the expected value of u hat is 0, right? It can really interpret it as a deviation from the expected value, which is here 0, right? And you get that always. It's always ensured if you regress, if this matrix of regressors contains constants. Again, that's also something you know from the bachelor, right? This variance percentage explanation of the R square is only valid if your regression contains a constant. Okay? Otherwise, the R square could even be negative also. Okay, what else can we say about the R square? Well, first of all, this is something you already know. You also know from the bachelor. If you look at this here, right, at the definition of the R square, then you see already that, well, especially at this here, maximizing the R square, so choosing the beta hats in a way that the resulting R square is maximized, is equivalent to saying choose the beta hats in a way such that SSR is minimized. Because the R square is just 1 minus SSR divided by TSS, you know, and this is here, that here doesn't change when I change the beta. This is just the variation of my endogenous variable, so it has nothing to do with beta, right? And here the SSR, this is that one here, these are the sum of the squared residuals, right? This is the length of this vector. So this here shows you that applying ordinary least squares is just really equivalent to maximizing the R square. Okay? So we could also derive this formula by the aim function maximize the R square. Choose beta in a way to maximize R square. That would be just mathematically exactly the same as minimizing the square deviation. Okay, that's the thing. So what does that imply? Later, I guess rather at the end of the lecture, we will talk about evaluating the model and which variables should we include and so on, right? And one very naive idea is, when you talk about how to specify your model, is choose your model in a way to maximize R squared. So in this, if you have your model with 10 regressors, and you think about, should I include an additional one? Well, one naive approach would be, come on, put it in, yeah, run the regression with these 11 regressors, and then look whether the R square increase or not. And if the R square increase, that's good news, because then the fit is better and blah, 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 and then obviously, the 11th regressor should be in the model. Now you see why that is naive, because R square will always increase if you include more regressors. It cannot decrease, right? Because least square estimation means choose a beta in a way that such that the R square is maximized. So if you have more regressors, then there's always option to improve, right? And of course it will somehow numerically a little bit improve even if you add another regressor, right? So the R square, the naive R square, is not a good statistic to decide whether I should include an additional regressor or not. Now it gives some, if the R square explodes, by an addition, then this is an indication, right? And if it does not change, it changed only in the 10 digits, this is also a strong indication, right? But just saying, because it has increased, obviously the variable from 14 is over. That makes no sense. All right. That's the R square, and this is, I would say, these are the main takeaways you should understand, or you should practice when you talk about these squares interpreting as a projection. Okay? We could talk a lot more about the mathematical properties of these projection matrices, and there was this slide here when I was a little bit shocked because you were too shy to answer my questions here about eigenvalues and all these things and traces. We need this, but we can postpone this when we need it, right? So I could now talk about traces and eigenvalues and all these things, but I don't want to be lost in math. Let's talk about the regression model, and when we really use this, then we or Leah or both, we will memorize you and we will introduce these concepts. These are not difficult concepts. Okay? So if you know how to invert a matrix and how to multiply matrices, then and to solve a polynomial for its roots, and then this is that's not difficult. You can do that. All right, great. Here's a summary, right, of this subchapter. So we assume that we know the data generating process, the DGP, right? So we just say this is what we need. And then, irrespective of everything, we just brute force choose the betas using the ordinary least square estimate, which is like this. And as we already said, this you can always do that, right? Regardless of any assumptions about the variables, you can always just mechanically do this if this matrix here exists. So if x prime x is invertible, right? Otherwise, you could do this as no. I can do this, right? And again, it's important that you know why that's the case. Okay. So what does it mean? In what cases is x prime x not invertible? And remember, I guess we had this slide. This one here, right? So mathematically, that means that one of the regressors is linearly dependent on the others. So you can express one of your regressors, one of your xk's here, as a linear combination of the others. So it's just a superfluous regressor. You don't need that. This regressor gives you no additional information, right? So besides any math, you know, it's a question, why should I include regressors that give me no additional information, right? And in fact, you know, if you just look at this equation and just, you know, think about, and just assume the extreme case that xk is just identical with x1. Yeah? Then you already see that it's mathematically impossible to distinguish between beta 1 and beta k, right? Because the regressor of the data is identical, so I cannot distinguish. I cannot say it's impossible to say this is here +1 and -1, or whether it's +2 and -2, because it's just identical. All right. We say that it's not identified in that sense, in that model. Right? Okay. So, of course, you know, the betas here, it's more easier to distinguish for that formula between the impact of the different regressors, the more different these regressors are. If you have three regressors in your model, but they are more or less identical. If they are exactly identical, then it breaks down, error, right? Then you can't put this formula. But what happens if you have this almost linear dependence? So if these regressors are very similar, right? A Keynesian consumption function where you regress consumption on income, yeah, and wealth. Income, wealth, highly collinear, hard to distinguish. People with high income often have high wealth. Not always, but you know, from a macro perspective. So therefore it's problematic, it's difficult to distinguish, comes that increasing impact on consumption now from the income, which goes up, or from the wealth, which goes also up. You know, how should I decide? How can I decide? What is actually the reason for the increase in consumption when both goes up? And this is exactly the problem of collinear regressors that are almost linear dependent. So this is what happens in practice. You know, and if we talk about this, right, you already can imagine what the problem is. Then, if you have a matrix here with not exactly, but almost linear dependent things. So if they're highly correlated, as in this macro example, right? Then this matrix here exists, but it's hard for the computer to calculate, right? Because it's close to non-invertibility, right? And that blows this matrix here up. It's like dividing by a very, very small number, right? So it gets to infinity somehow, right? And it's very similar here, right? If this is here nearly not invertible, then this goes here, this gets large. And what we see in the next chapter is that this means that the variance of the beta hat gets huge. So this matrix here and the variance are naturally related, you know, because if I can't distinguish between two estimators, obviously the uncertainty about the individual estimators is high. And this is exactly what's in the variance matrix of beta hat. Okay? So that was the only assumption we need. Where we are here. Here we are. So we also rely on regressions that have a constant. So only in that case, you know, it is assured that the average of the estimated error is really 0, and that we can really use this very efficient decision and interpret the R square the way we want. Okay? I'm not aware of any empirical applications where it does not make sense to include a constant. The only applications I know is where in the first step each regressor and the endogenous variable were adjusted for these, right? Then of course we don't need a constant, because we know already that the constant is 0. Right? This is the only application I know where it's really important to throw that constant out. Right? Otherwise, I would always opt for a regression with a constant, because it's just controls for differences in the means of regressors. It doesn't do any harm. Okay, this is the orthogonal projection thing that allowed us to concentrate our regressors and also talk about the difference. Okay, this is a summary of what we did so far in this subchapter. What we do now is we talk about probabilistic statements. So far, we just derived the point estimator. We said beta hat is something, 3.7, right? But we could not answer about, well, how uncertain are you about that? Could it also be 3.8? I don't know, right? Maybe, right? So in order to answer questions like this, to derive confidence bands about our estimation, to talk about estimation uncertainty, we have to talk about statistics. So, therefore, chapter 3, let's talk about the statistical properties of ordinary least square estimation. Okay. And here's an overview here, what's all about in this chapter 3. So, again, we are in the linear regression model, and we start with a very strict assumptions about the stochastics here. We say, okay, now we may count on the fact that the deviations from our models are somehow stochastic, that they are random variables, right? And we have a model for this random variable, because if you want to talk about uncertainty, we need a model for that uncertainty, otherwise how can we talk about it? So the assumption here for the moment is that the U's here are somehow distributed. There's some distribution, here, random. The expected value of the U's is 0, because they are errors, come on, right? They're errors, they're deviations from the true model, so the expected value should be 0. And there is a covariance matrix of these U's. And look, this is an identity matrix of dimension n. We have n observations, so we have n U's, U1, U2, U3, blah, 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 Un. And this is an assumption about the covariance of this vector of n random variables. So how does my random deviation in observation 1 correlate with my random deviation from observation 2? Right? So it's more easy for me to think about time series observations here, right? But you can also translate it as a cross-section, that's not a problem. So if you have n periods, right? And U1 is the error, the random error you make when you do your forecast for the first period, U2, second period, so on and so on. What this here tells you is how are these forecast errors of different periods related to each other, right? Now assume they would be, for example, positively correlated, right? What would that imply? Suppose I make a positive forecast error in period 1. Okay? What would that imply? The man who's just checking his Snapchat account.
No. So I'm not checking.
You are checking my Snapchat account?
Might be going to.
Okay, so you have a positive error in period 1, and the errors are positively correlated, just suppose, right? What does that imply for your forecast error in the second period? Yeah?
That the error is larger than the period prior?
No, but it's larger than the average, right? So on average, everything is 0, right? And now you observe in the first period a positive value, so it's above average. Today, above average. What does it imply for tomorrow, say, right? If the errors would be uncorrelated, the answer would be nothing. Well, today I overestimated GDP or whatever, right? What does it mean for my forecast error next quarter? Nothing, because nothing if the forecast errors are uncorrelated, right? But now assume they would be correlated. positively correlated. Today I overestimated GDP. I'm the forecaster at DRW, and I overestimated GDP. I have a positive forecast error. Now assume I would know that forecast errors are positively correlated. What would that imply for my forecast error in the next period? It would also, there would be a chance larger than 50%, because of correlation, that if I overestimate this quarter, I will also overestimate next quarter, right? Because they are correlated positively by assumption. Okay? And now assume you're working for DRW and your job is making forecasts for GDP, right? And you know, for whatever reason, maybe because you estimated from the past, that your model produces positively correlated forecast errors. That's a shame, right? I would fire you, probably, right? If you wouldn't react to that, right? Because you make a forecast error and you already anticipate, you know that, yeah, today I overestimate, my best forecast, I will also overestimate next quarter. What? You know already that you will overestimate and you do not respond to that? Well, obviously this is not optimal forecasting, right? So this is why one check of optimal forecasting is, or rationality of forecasting is looking at the forecast errors, realized forecast errors, and checking for correlations, right? And if you can explain forecast errors, that's always a bad news for the forecaster. Yeah?
But I don't really understand, because shouldn't, by assumption, the correlation between the errors, shouldn't it be zero? Because
the expected value is zero. What we say here is, yeah, exactly. We assume here that there is no correlation between the errors because the covariance matrix is diagonal. What I just want to say is, that makes perfect sense to start with such a model. Because in the forecasting example, it would be stupid to have a covariance matrix that is not diagonal. This is what I want to explain. To make sense out of that formula. Right? If you have such a thing, then you have uncorrelated errors. Because the covariance matrix, remember, covariance matrix, on the diagonal you have the variances. The variances are sigma squared. And on the diagonal you have the covariances between the things, between the errors, for example, here. Right? And what this assumption tells you is these covariances are zero. Because it's a diagonal. Diagonal means the identity matrix has zero on the off-diagonal elements. So here we assume there is no relation between different errors. Yeah? This is what we assume. What I tried here, the last 5 minutes, is to convince you that this is a very natural assumption, a very natural starting point. Because if it were not like this, if you would have a correlation between the errors, then in the forecasting framework this would lead to these strange implications. Yeah? Alright, so we start with very nice looking views. Yeah, these are the assumption of a standard linear regression model you should know from the bachelor. Right? We have homoscedastic errors, so the variances are all the same, and we have freedom of autocorrelation, so there is no correlation between the errors. Okay? So that's the starting point. And we derive the assumptions of the OLS estimator under these assumptions. Okay? And we discuss, of course, what will happen if these assumptions do not hold in our example and how we can detect it. Okay, so here are one or two slides explaining you why it is important to talk about statistics in the context of linear regression. Remember, here, no statistics, no variances, no expected values, just math, brute force math, suck. We just calculated these numbers. Bam, that was it. Right? In economics, however, we want to talk about marginal effects. We want to interpret these betas. And we are obviously interested in answering questions like, yeah, we estimated 3.7, as I said, right? Could it be also 3.8 or 4 or 5 or minus 7 or what, right? Just applying the math without assumptions about variances and so on, about use, we can make no statements about estimation uncertainty and confidence bands and testing, and all these things are not possible so far. Okay, we need statistic assumptions. And the same here, right? If you want to use these models for making predictions, for forecasting, then again, right? If you say next quarter GDP is 1%, then the natural question is, how certain are you? Could it be 2%? Could it be minus 2%? Well, and if you say, I don't know, this is just a number which my computer pops out, how should I know? Right? Then not good. Right? You have to make a statement about the uncertainty and the certainty of your estimation. Okay? And in fact, you know, the educated concern, and nice, the educated concern, so this is obviously not my English, right? About what is distinguished econometricians from the machine learning camp. If you're a machine learning guy, you don't care about statistics, actually, right? You just want to make forecasts, right? And you compare your forecast with your, you know, you have your training sample and the evaluation sample, you know, and if it works, it works. If you ask a machine learning guy, why does it work? He shrugs. He don't care. He don't want to understand dynamics, processes, who is responsible for what. It just should work, right? That's machine learning. It's a black box. Okay? Very efficient for many applications, but if you really want to understand what's going on, no, not very helpful. Okay? So they are now, you hear about causal machine learning and all these things, these are first steps to make sense of the result of machine learning algorithms. Right? But it's a long way. And these steps are, coming back more and more to standard econometrics, actually. Yeah, but that's different thing. Okay, so we want to understand the facts, we want to talk about elasticities, and we want to interpret the betas, and we talk about can that beta be 0 or not, or something like that. So we're out of the machine learning camp, using econometrics. All right, here's a very general thing, right? Just to say a few general words about the properties of estimators. Okay, so look here. This is a notation in David's McKinley as it goes. Theta hat. This is the estimator of an unknown parameter theta, or parameter vector theta, that doesn't matter. Okay? So here our theta was beta. Okay? So, and of course, the result we obtain from our estimate somehow, as in the least square example here, somehow depends on the regressors, on the observations we get. Okay? Therefore, theta hat depends on x. Yeah? And our parameters are theta hat are the estimators that are obtained here. So beta would be theta, and beta hat, here's the formula for beta hat that depends on x, as you can see, here would be beta hat. Right. Now the first thing is that you should understand, so these x1, all these regressors here are random. Right? So this is, everything here is random. So also the result of my estimation is random, especially because the y is random, by the way. Okay? So what this slide here wants to, wants to remind you is that you should distinguish conceptually between the estimator, between an estimator and the estimated value. Right? So far we only talked about the estimator, the least square estimator that was given by that formula. So, and you see, we talk about a function somehow, right? So whatever y and x is, just tell me, and I know the principle of least square estimation, and I can calculate the corresponding beta hat. Right? So this is the function, the estimator. And that is a random variable because it depends on the randomly chosen data. The estimated value. However, this is just a number. This is 3.7. Whatever my observations here, when I plug into the formula, the result that came out. Looking at right? So the 3.7, which is the result of my B-square estimation, this is not random. This is a number, right? But the function, the idea of B-square estimation, this is a random variable because it doesn't give me a number, it gives me a functional relationship. Give me your random observation and I tell you what is the value of the estimate. Okay, so here are a few examples, and this somehow explains why it makes sense not to talk directly about beta, but also about why we call it more generally theta. Okay? Of course, you know, if we want to estimate the slope coefficient in a regression model, then theta is beta, right? But maybe we want to also estimate the variance here in our model. So we don't know the variance, maybe we have to estimate it, or the mean of the variable. You know, here the well-known t statistic, right, from angiometrics, which is more or less estimated coefficients divided by estimated variance. This is also a test statistic. This is also an estimated value, sorry. Okay, so we have many examples, and there are much more of them later, of these estimated parameters. Okay, so different estimation methods for theta may correspond to different functions, of course. Statistical properties estimates characterize how good they perform in estimating. Okay, now we have this function here, for example, here, this estimator, and we want to know how good is that estimator. Well, so we derive on the next slide some criteria to evaluate whether an estimator is good, is feasible, what are the properties of that estimator. In the following, we will distinguish between finite sample and asymptotic properties of the estimator. Well, it goes without saying, finite sample is how does that function here, for example, here works if we have a finite number of observations. And what happens if we think about these properties if we assume that this n goes larger and larger and larger and larger and larger. Those large sample properties or asymptotic properties. We will see that this makes a difference. So here are the classical assumptions of a linear regression model. Right? If you look at your bachelor thing and your bachelor notes, you will recall that. So first of all, what are our assumptions about the data generating process? First of all, something which is sometimes forgotten, right? We make here very strong assumptions that we know the functional form. So we know what kind of regressors are relevant, and we know it's a linear model, right? Okay, so we don't talk about, we have no clue how these variables are related. Yeah, you have to check logs or somehow squares. No. This is postponed. Assume we know this is the true model. Okay. Next thing, because we want to talk about the square estimation here, this means the well-behaved limit. Well, first of all, this means that will mean, first of all, this matrix here will be will still be invertible, because otherwise we can do this, right? So we want that x prime x is always be invertible. And the second thing is that it will be finite. Finite? Why is that necessary assumption? Look at this here. X prime x. What is the dimension of x prime x? It's a matrix, it's a quadratic matrix, symmetric matrix. What is the dimension of it? 1 times 1, 2 times 2, n times n. Yeah?
K plus 1 times k plus 1.
Thank you, perfect. Look here, if we have k plus 1 regressors, it's a k plus 1 times k plus 1 matrix. In geometric textbooks, this, whether you call it k plus 1 or k, that depends on the notation, right? But it's finite. It depends on the number of regressors. It's a small number, right? If I estimate a model with 3 regressors, the x prime x has a dimension of 3 times 3. And look, it has a dimension of 3 times 3, even though n can get as large as you want. So you have 1 million observations. If I have 1 million observations, then if I go to R or Excel or whatever where my data is, I have for each of the regressors, 3 regressors, 1 million observations. So the x prime or x matrix has a dimension of 3 times 1 million. It's a super huge matrix, right? So, not interested in x prime for estimating, I'm interested in x prime x. So what I'm doing is I have this huge matrix, and I multiply it with Posen, and then multiplying out of these 2 huge matrices, huge dimensional matrices, gives tiny matrix, 3 times 3. Yeah, because this million just cancels out, right? So the dimension, that's obvious. But imagine what you are doing. You're multiplying millions of numbers and adding up. This is how matrix multiplication works, right? So it's far from obvious that the numbers that are in this x prime x here, they are a convolute of a million, they might be huge numbers, I don't know, right? So you have, if you want to deal with that, if you want to do something like x prime x inverse, you have to make clear that this is well behaved. In 2 dimensions, the 1 dimension is obvious that it's not blowing up everything, right? Because you don't want to divide by infinity or something, right? But you also want not to divide by 0. So it's also, if n goes to infinity, it is not good when it goes too small somehow, right? So this is what well-behaved means. We will see in a minute, more precisely in the proof of consistency, where we need this assumption. Okay. Very important block here is the assumptions about U. These are typically the assumptions we talk a lot about in bachelor econometric thing, right? So you know that no autocorrelation of residuals, no heteroscedasticity. This is the diagonality of the covariance matrix here. And sometimes we assume for simplicity that the distribution of the errors is known. And then we say, okay, let's suppose they are normally distributed, right? Not so super important. This important thing is we have to discuss now this one. In bachelor, I teach bachelor mostly, or the most part of it, assuming that the axes or regressors are non-stochastic, or not random. If they are not random, right, and you have a random variable and a not random variable, then more or less by construction, these strict exogeneity assumption is there, fulfilled, right? Because if you have something which is random, it cannot be correlated with something which is not random, right? This is why assuming in a bachelor econometrics books that the regressors are non-stochastic or not random simplifies all the proofs and everything so immensely, right? Because then you really have strictly exogenous regressors. And this implies, this means this here. The expected value of the U for given x is always 0. Whatever happens, whatever you assume about x, always 0. And this is not only true and this is by construction true for non-stochastic regressors, but here we assume it should also hold under strict exogeneity for stochastic regressors. If this is the case, if we just assume that, for example, this implies that the expected value of the U's are 0. And look here, this needs some explanation here. This means, remember that the expected value of the product of 2 random variables is more or less a covariance. Right? Covariance of xy is expected value of x times y and then minus some constants. Yeah? So this is 0 is equivalent to say that the u's are uncorrelated with the regressors. Okay? Okay, but, and this is why it's here j and I, right? So this means here for all j and for all I. So the residuals ui are uncorrelated with all regressors, the whole vector of regressors. And this here, and this is something, so this is an implication of this strict exogeneity. And recall, in bachelor econometrics, if you just assume that x is not stochastic, then yeah, why not? Because this is a random variable, this is no random variable, so of course they are uncorrelated. Right? So you can just, if this is not random, you can say this expected value is the expected value of ui times x, and ui 0, so it's 0. Right? If you assume not randomness for the axis, this is by construction given. No problem. Strict exogeneity is clear. Bam. But the problem is that for most applications is that this strict exogeneity rules out lag y in x. And lag y in x, this is super important for time series analysis. So whenever you have dynamic adjustments, so when today depends somehow on yesterday, you want to have lag endogenous variable under your axis. So something like yt is alpha plus beta 1 times yt minus 1 and so on. So today depends on tomorrow, on yesterday. And if that happens, then there is a correlation between the u's here and between the regressors and the u's of yesterday. I don't know to see whether I can convince you of that easily. So here, if you have something like that, ut is alpha ut minus 1 plus ut. Yt is alpha, yeah. This is a simple linear regression model, but the problem is now we have a lag endogenous variable. Okay, so obviously, assuming that the regressors are not random makes no sense, right? Because if this is a random variable, then of course yt is a random variable. But if yt is a random variable, then of course yt minus 1 is also a variable, because we can write this equation, of course, also holds for yt minus 1. Okay? Obviously. So therefore, random regressor. And now the question is these regressor matrix, which contains select values of the endogenous variables, does this fulfill strict exogeneity assumptions? And you see, obviously not. Because this here is correlated with former u's, right? So obviously, ut minus 1 affects yt minus 1. Because yt minus 1 blah, 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 plus ut minus 1. Okay? So therefore, this affects this, and this is the regressor here. So obviously, we don't have that the regressor in period t is uncorrelated with the residuals before. There is a relation. This is why strict exogeneity is not a good assumption when we deal with time series, with lag endogenous variables. Okay? Well, that's a super strong assumption, which makes sometimes sense, right? Particularly deal with cross-sectional data, but it makes definitely no sense in time series analysis. Therefore, we are all relieved that there's a weaker form of exogeneity, which helps a lot, especially if we have large samples. So, weak exogeneity looks very, very much the same, but the point is now that this uncorrelatedness of U and the regressors only apply for the same I. So the only thing we want to have is now that, not that the ut minus 1 is uncorrelated with all the u's, which is obviously not the case. The only thing for weak exogeneity we want is that the ut is uncorrelated with the same yt. Here, that the ut is uncorrelated with yt minus 1 here. That one, sorry. Yeah? This is the regressor, this is the x, and this is the ut. Okay, so xik in this example is yt minus 1. And that is a much weaker. Here, look, strict exogeneity means this is uncorrelated with all the u's. And weak means no, it's okay when it's uncorrelated with the corresponding one. This is called weak exogeneity. And this allows for predetermined axes. Right? This is not a, so if we have, that this is here uncorrelated with that, then this is not a problem. So we have a lag, a predetermined x, but still weak exogenous regressor. Okay. So what we do next? What's the plan now? Now we have set up the statistical model for linear regression. That is known because it's actually and now let's recall criteria that we use to evaluate an estimator. And the first criteria is the bias of an estimator. Okay? So what we want to have is we call an estimator unbiased if its expected value is exactly the same as a true parameter. And you know that from square estimations, you sometimes have, I bet you proved in your agrammatic that your expectation of beta hat is beta. Yay, unbiasedness. All right, so you see that this is a finite sample property of an estimator. So you have n observations, 100 observations, and you can prove that in that case, under some assumptions, the square estimator is unbiased. So if this bias here is a bias, which is just the difference between these two here, is different from 0, the estimator is said to be biased, okay, systematic error. Okay, what is the interpretation of that? Biasness or unbiasedness? So why is that a good idea, Look, we already talked about, I guess, about the interpretation of the expected value as the average value. If you repeat a random experiment, and for each repetition we write down what the result is. Unbiased, this means that on average our estimator is close to the true value. There is no systematic under or overestimation. On average, I'm right. Okay? So if I do the Gedanken experiment, then I could repeat my estimation 1,000 times. If I would do that, and I take the average, then I'm close to the expected value. Okay. I have to apologize a little bit for potential repetitions, because I also teach Introduction to Time Series Econometrics in the bachelor. And of course it also builds on Econometrics 101. And also there I have to remind people what an expected value is, what the variance is, what the covariance is. So sometimes I'm not sure, did I make these examples in the bachelor thing or here? Okay. So expected value thing, right? Just as a quick reminder, right? If you have a dice, a fair dice, number 1, did I do you remember that? Okay, so I did it in the bachelor. That's all. So you have a fair dice, numbers 1 to 6. Probability for each number is the same, right? What is the expected value of the dice? So, yeah?
3.5.
3.5. Yeah? 6 times 1 plus 1 over 6 times 3.5. What is the probability to observe 3.5 when you throw a dice? 0, right? Because 3.5 cannot happen, right? So, if you ask someone what is expected value, what does that mean? And that someone told you, you know, expected value, that's the value with the highest probability, you see immediately nonsense. No. Yeah? The probability of observing 3.5 with a fair dice is 0. Still, it's the expected value. So how can we interpret 3.5? And this is the Duncan experiment, right? If you throw it 1,000 times, and if you note the numbers you threw, right? And then you add up and divide by 1,000, then the number is super close to 3.5, right? This is the visualization, interpretation, illustration of an expected value. All right, so on average, there's no systematic over and under estimation. Okay, and here you see, I don't know how useful that figure is, you know. Look, here is a true estimated. Here's our estimated parameter, and you see, if we do this, if we make an estimation, right, and it's random, then there is a distribution of that random estimation, right? And this is and the mean of this would be our estimated parameter. So if the true parameter is like this, then obviously we have bias. Okay, I don't know. It's a nice figure, but I don't know what extra insights are supported by that. All right. Here is the theory in our application. Okay, so which shows you the assumption under which the least square estimator, beta hat, is unbiased. It has no systematic bias. And you see a little bit awkward here, but the main assumption here, what you need is, as you see, strict exogeneity. Okay, if that's the case, then look here. This is the formula of the least square estimator. Here we just inserted y, right? Y is x beta plus u. If you multiply out, you see that your least square estimator beta hat is nothing but beta, the true value, plus this, right? Whatever that is. Unbiasedness means expected value of this is just beta. And you see, if you take the expected value here, beta is just a number, so the expected value of beta is beta. Yeah, like the expected value of 5 is 5. It's not random. What you see is saying that the least square estimator is unbiased is equivalent to showing that the expected value of the second part here is 0. Okay? So, and here's the proof, and you see it's a one-liner. Right? So, the expected value of beta hat given x minus beta, this is the bias. This should be 0 if it's an unbiased estimator. If you subtract beta hat from beta, the only thing that remains is this animal here. So this sum is just this here. Nothing happened so far. We just plugged in what we know from the model. Right? Nothing happened. All right. Now, it comes. So we say, well, expected value of this given x. So we take the conditional expectations on x. Therefore, we can treat the x's as given. And therefore, we can pull out this formula here out of these expectation operator. So this is exactly the same as this here. Yeah, because we take the conditional expectation. In the bachelor proof, we just say, oh, x is not random, so we can just put it out here. And that's it. That's the proof, more or less, right? So here we have to argue with the conditional expectation on x. So this is what's left. And here you see, here, when is this always 0? This is always 0, if and only if the expected value of u given x is 0. And this is, bam, exactly our assumption on strict efficiency. So, least square estimator is unbiased if and only if the regressors are strict exogenous. Okay, and here's a reminder. This is in many applications a weird assumption, especially when we talk about time series models and that endogenous variables. Right? So it might be realistic for cross-sectional data, but not for time series data. So this is bad news, right? So this already implies if we run a least square regression on a very simple model like this, the least square estimator is a biased estimator. Full stop. Yeah. That's bad news, and we have to think deeper about that. But there's also good news in that proof. If you look at that proof, you see the other assumptions we made, especially on the errors, like there is no autocorrelation, there is no heteroscedasticity, blah blah blah. They do not show up. We don't need them, right? So if we would show the and you know what, the U's are autocorrelated, and who, they're also heteroscedastic, that wouldn't change anything in the proof. So good news is, if we have strict exogenous regressors, then the least square estimator remains unbiased, even in case of autocorrelated heteroscedastic regressors. Okay, and this is exactly the same result we have in the bachelor when we talk about not random regressors. Okay, so let me just show you as an illustration. Or was that just a question? Here, what this bias means. No, I don't want to hurry up. So let's take some time. Okay, so what I want you to do is, however, to think more about these unbiasedness. And I have one slide, and that was actually my aim today. Right? This is where I want this. Right here. Here I have 4 strange examples for estimating. Look here. I have n observations for y, and they're all IID, right? And I want to estimate the mean of that, the expected value of y. Now, the expected value is this is mu. Well, and this is what I want to estimate. And here are 4 suggestions on how to do it. Of course, we know the best way to do it is just take the average. Yeah? Just take the sum and divide by n. That would be the best idea, right? No question. But now, check whether these estimators here are biased or unbiased. Right? So take the expected value of this and check whether the result is mu or not. If it's mu, unbiased. If not, biased. Alright? We will come back to these examples when we then, next week, talk about asymptotic properties. So then what happens with that bias if n goes to infinity? We have large samples. Okay? Thank you. This is for today. We'll see us next week.